Here we are once again. This is the Physics 2A video lecture 8. Physics 2A video lecture 8. And I'm going to start with some announcements. We have an exam this week. So Thursday, for the Tuesday-Thursday group, I'm going to send out the exam by email at 5 o'clock, and I'm going from 5 to 7 o'clock. So we want to get them back after 2 hours. You know, it'll have a timestamp on it. And for the Friday group, same type of exam, same 2 hours to get the thing back to me. Friday it'll be 8 to 10 a.m. So that'll be interesting, to say the least. What else have I written here? Make sure your work is legible, and when you send it to me, you know, in your subject line, make sure your name, that it says your name, 2A exam, and what section you're in, Tuesday, Thursday, or Monday, Wednesday, Friday, and that way I can sort them out easy enough. As far as them being legible, you want to test it out. Most of the homeworks that have been sent to me are very clear, but you know, I said just spread your work out sometimes, and of course for the exam you want it to be, you know, one page at a time and very clear, because I'm going to be grading them, looking at them on my computer screen. Okay, but that's all going to work, and make sure you have that dialed in by the day of the exam, that you know how to send something off like that. What else do we have? I decided to spend some of today's lecture talking about thermal physics, the new chapter, because that way I can show you a few demonstrations, and some of it actually will tie in nicely to stuff we've done before, even though it's a pretty new subject. But then we'll go and review chapters 6 and 7. The second lecture this week, which should be out no later than Tuesday evening, we'll review chapters 8 and 9. So we're going to review these things pretty thoroughly. Chapter 10 that I'm going to start now won't be on the exam, but of course it'll come up later and it'll be there for you to look at, whatever I do today. And the notes are due on Friday. So the notes from these two video lectures coming up, lecture 8 and 9, are due on Friday. And I'd like to say the notes that came in were excellent. I saw so many great notes that people seem to have taken a lot of time, and that's important because really it's, you know, it's your show in terms of how much work you put into this, and it was pretty impressive. So keep up that work, right? Keep up that work. We're going into the final stretch. This exam's going to be, you know, a test for how we can pull this off on the final, but it's all going to work. And so just keep working hard, take good notes, and now that I've seen it, I know it can be done. Very nice. Good. Pardon. So those will be due on Friday, which will be after the exam. You can, you know, by the way, these review notes I'm giving you, I hope for them to be very useful, very, very useful. Good. So, and you know, I can repeat these things in the next video lecture, and of course, I'll be emailing the exam to you, and I'll be talking about that more, and I'll send you another email for a general heads up. Okay, so we'll be plenty informed on all this. Okay, I'm going to send this up. Another interesting thing is we have a lot of glare in this room, but the lower board is pretty glare free, and I sent it up to the upper board. It doesn't seem to be that bad. Okay, so let's just take, I don't know, maybe 20 minutes for the thermal physics, and I'll show you a couple of interesting demonstrations. So we'll start with thermal physics, and there's a way I like to present this, real good logic to it. So the first thing with thermal physics is that we're just talking about the sensation of hot and cold. Literally just the sensation of hot and cold. So sensation, hot, cold, okay? And what you feel in your skin, okay? And these sensations or associated with phenomena. So I'm going to write here next is the associated phenomena. That go with the hot and cold, and yeah, you could say hot water and cold water. You could say fire and ice, right? Those are phenomena that go with this sensation. So I'll just write fire and ice, etc. And so I brought an example of fire here. I brought a torch. You have a torch. I have a flame here, and this is truly hot. Now, even though we're kind of far away from the camera, this won't be a close-up, but there are a couple of interesting phenomena. That we traditionally always demonstrate. And the first one is about thermal expansion. So we have a number of these backstage here. So this is a brass ball, and it doesn't quite fit through this ring, okay? If you were just to look at them or hold a ruler to them, you wouldn't really be able to tell. They're pretty close in size. And so what I do is just heat soak this one in the flame for a couple minutes. You're gonna have a little patience. Get this thing hotter, and we're not actually going to see any change in this thing. There's hot flame on this. I gotta be patient too, right? Because I'd like to give it a try, but give it a little extra time here. Definitely don't touch this thing, right? It's been in a very hot flame. Let's see. There we go. Okay, so what happened? This ball, which wouldn't pass through before, now passes through. This thing has expanded ever so slightly, but sufficient to allow this to pass through. Okay, passes through easily now. Okay, so that's what we call thermal expansion. Like I said, if you look at it, it looks exactly the same. Held up to this ruler, not going to make much difference. You're actually not going to see it. It's a fraction of a millimeter. Okay, but it definitely expanded. So that's an important demonstration. In fact, if I were to hold this thing here too long, this ring will contract onto that, and we won't even be able to separate them anymore. It's kind of a problem. So don't be tempted. So we have thermal expansion as our phenomenon. So we had fire, and then we see that fire applied to a metal expands the metal. Okay, so I'll just leave this right here. Okay, here's actually a humble looking object. This is a strip of metal. Seems to have a slightly different color on one side. The effect that I'm going to show you here is when I apply heat to it, it bends. Now you wouldn't just recognize this as thermal expansion unless you knew that it's actually two thin strips of metal that are sandwiched together. And what's happening is one metal expands a little more than the other and pushes it into a curve like that. Okay. Let me write these things down. We have thermal expansion. Thermal expansion. And for the demonstration, you have the ball and the ring. And, they're both on a handle. One of them's like this, and the other one is solid. Okay. So you have the ball and the ring, and what happens there. And this next demonstration that I just did, or the second one that I just did, is the bimetallic strip. Bimetallic strip. And there we have on this handle really just a strip, but if you know what it's made of, they're two different metals, and therefore when we apply heat, one side expands more than the other, and the thing actually bends over like that, okay? So this is a little less controlled actually. With this bimetallic strip, you can now imagine me putting a scale here, and apparently I've just designed a thermometer, because when it's pointing straight up, that was room temperature, and over here was hot. And I could show you later, if I had some liquid nitrogen, that it would bend in the opposite direction if it's really cold, okay? So here's the progression of ideas. We've got the sensation of hot and cold, we've got these phenomena, and we have this particular phenomenon of thermal expansion, and the thermal expansion allows us to have thermometers. So in this progression here, we're now going to write thermometer, and that's just some object that makes use of a physical property to tell you whether you have hot or cold. Okay. But that also sounds a little vague, but you know, I said room temperature and hot, and this was as hot as a flame, but if I could control this and put a scale there, then I would have what's called a temperature scale. And oh, here's a thermometer right here. It's not a clock, right? It's a thermometer. It's saying it's degrees Fahrenheit on the outside, so it's saying around 60. I don't quite trust that. I don't think it's quite that cold in this room. But how does this thing work? How does this thing work? Can I change the temperature on this? Maybe. What this thing has on the back is a bimetallic strip coiled up in the middle. Coiled up in the middle, and to really give it a little gusto, I'm going to give it a burst of flame. And that bimetallic strip expanded as it does, and suddenly it's reading 100 degrees. Okay. So there's a thermometer that makes use of the bimetallic strip. Legitimate thermometer. Okay. So what other kind of thermometers do we have? Let's go ahead and send this up. Thermometer. Okay, I'm going to erase all this. So what follows on the idea and the reality of a thermometer, and maybe I'll draw a couple of those, or you could draw a picture in there of what we're thinking of when we have a thermometer. We're making use of thermal expansion for our thermometer. Okay, what follows on that is the temperature scale. Okay. So next in line here, 4, temperature scale. I just kind of illustrated what we would do with our bimetallic strip, and that, you know, that is exactly what we did here, because this thermometer had a bimetallic strip in back. It wasn't just a single, you know, it wasn't just vertical, it was a whole coil of it, but that was essentially what happened when you heated it up. It turned one direction, you cool it down, go the other direction. Okay. So another type of thermometer, of course, is the, should I put that up there? Well, I'll leave that for the moment. The idea with temperature scales, what I can do is draw my thermometer right here. So I'm going to draw a really tall capillary with a reservoir at the bottom. Do you have any colors today? Let's see, yeah. Capillary with a reservoir on the bottom, and I brought something like that as well. So we have a fluid in here, and the fluid experiences thermal expansion. And so you have a column here of fluid that reaches a certain height. and no higher. And then we can have a scale. And if this were degrees Fahrenheit, we would have two phenomena that we nail it down with. We would say ice melts, and that would be 32 degrees Fahrenheit. And up here somewhere, we'd say water boils, and then we would have 212 degrees Fahrenheit. But we could take an identical thermometer. Hey, didn't I bring one to show you guys? Yes, these may not be as in style as formerly, but there is a thermometer, okay, and it goes up to 100 degrees Celsius. So I'm going to introduce the Celsius scale next. Okay, you've got a thermometer there. Put it in something. So yeah, I could have the idea is I could have this little beaker full of ice water, and then my thermometer would measure 32 Celsius, but Fahrenheit, but since we're talking about Celsius scale also, I can just draw a second thermometer. That's how I draw it. Put some of this fluid that expands thermally inside. Call this the Celsius scale. And then identical thermometer, and I've just changed the scale because now I have 100 degrees Celsius and 0 degrees Celsius for ice melting and water boiling. So you can see at this point we could make up as many scales as there are names in the phone book. Just stick with these two for now. But yeah, there's an example of thermal expansion in temperature scales. The conversion of these I could do, I may save that for some other time. The conversion between them, nowadays everybody just types it in and finds out how to convert these. But it's actually, we'll do it now. Temperature conversion. I should assign this as homework. Temperature conversion. One thing we can do is this. We can say, okay, I've got a degree Celsius scale, I've got a degree Fahrenheit scale, and at the 0 here, I know that ice melts, and at the 100, water boils. Okay. What about Fahrenheit? Well, there I've got my 32 and my 212. Shows different scales. Okay. Here's the thing. If we assume a linear relation between the two, and we can do that because we had these thermometers that we just gave different scales. Then from this straight line graph here, you can actually derive the temperature conversion. So if you look up the conversion formulas, you can find them. I'll save them for you. You can actually just do the point slope formula that you learned in algebra at some point, and this will give you your temperature conversion. So good, I'll leave it at that for now. Good, so we've got, once again, had the sensations, we have the phenomena, thermal expansion gives us a thermometer. You got thermometers, we can become more precise and just define these temperature scales and gradations. Okay, I have one other interesting device that is a thermometer and more. I'm going to bring this thing out. So, in fact, this goes in here. In fact, to complete our little set of ideas, we could put this thing in here. Let's see how this is going to look to you guys. Yeah, so what is this? Okay. So here we have opening to the atmosphere, okay? And then this is the tube, glass tube, opens up to a little ball there, glass tube goes down. To here, there's a reservoir with some red fluid. That's connected via this tube to this right here, which is sealed. And the whole thing has atmospheric pressure, and right now it's at room temperature. So this can also be thought of as a thermometer, because if I heat, suppose I were to boil water in something here, and this were to read 100 degrees Celsius boiling water, then the increase in pressure, and this takes us to our pressure chapter, the increase in pressure in here, gas pressure, would push down on the fluid and would push the fluid up into here, okay? Atmospheric pressure being the same, increased pressure because the temperature on this side. In fact, you can use a device like this to learn about the ideal gas law. There's another interesting thing. Should be careful when I do this because I can't really see it. But if I blow air across this at an angle, not into it, but just across it. So I'm going to blow air across this, and this will take us to our Bernoulli effect. Remember, Bernoulli's equation said that when the airspeed is high, the pressure is low. If I blow air, and I gave a demonstration with those 2 sheets of paper the other day, okay, 2 sheets of paper. You blow between them and they get pressed together. So if I blow across this, and this is actually what this thing is designed as, the pressure here is decreased, the pressure here is unchanged, and it will also press some of the red fluid up there. Okay, so let's try this. I won't even know how well it works till I view this footage, view this film video. Okay. It must be working. I see it oscillating down there. Okay, that's the demo of that. So that's for the Bernoulli effect and the decrease in what is normally atmospheric pressure here by blowing across this little opening. I'll bring my torch in and just do the effect that we're looking at as a thermometer. You know, if I were patient, I could actually hold this in my hands and it increases the, well, I am patient, am I not? Look, I just hold this in my hands and it increases the temperature enough to bring that fluid up. Of course, I brought my torch here. Okay. So there you saw the effect, okay? So this is what we call, let's give it one more shot. Okay, that was real, right? And it cools down again pretty quickly. Good, no problem. So, that was what's also referred to as a gas thermometer. Yeah, it's one of the reasons I brought this in today. I wanted to get us up into this level of the discussion. So this last point I'll put here is the gas thermometer. You've seen it now. I can refer to it. Next week I can sketch it, talk about it, and so forth. We've seen the demonstration. Gas thermometer, and here I'm just going to put a hint used to determine absolute zero. To determine zero temperature on the Kelvin scale. Kelvin scale. Okay, let's put this away. And so that's an introduction This is an introduction to thermal physics. Hot-cold sensations, these phenomena, and all the way up to the temperature scales. And you know, because I showed you the gas thermometer, I have tied it into the other physics we've done before. The thermal expansion is actually something completely new. It's not part of the mechanics we learned before. The gas thermometer, and also its Bernoulli effect that it also demonstrates, that's part of what we did last chapter. Okay, so there's the connection there. The connection that's going to come later is the connection between these concepts and energy. Right now we don't have any connection to energy. You know, before we leave that subject, though, I'll state one. The connection to the energy concept is going to be heat, that we talked about briefly when we had friction. At the time, in the earlier chapters, I said, well, we can't really account for thermal energy yet, but this is what we're going to have when we get into this chapter. Okay, so let's draw a line under this now and call it good, and then we'll begin our review. Okay, this can stay here. Okay. I'm going to erase everything. Okay, so the next half hour we'll start talking about what we want to find on our exam. And we're just going through everything since chapter 6. Then this next lecture coming up later this week, I will finalize the whole thing and the instructions. But for now, we're just going back into the review. And you're going to see these reviews, and also for the final, they're just so valuable because the repetition is what helps us learn this material. So you see it often enough and work on it often enough, and it just makes more sense each time. You pick up these skills as well. Good, so let's call this exam review. Exam review. And here, chapters 6, 7, 8, and 9. And today I'll definitely talk about 6 and into 7, and then I'll pick up the rest next time. So for chapter 6 we have, remember this was linear momentum and collisions primarily. I'll just remind you of the concepts. The first thing we had was impulse, and its definition, I'll just call it I is equal to F delta T. So its units are newtons times seconds. It's most often used when you have a short time, a force that's just exerted for a short time period. The impulse equals the change of this quantity mv. I can actually put a vector on it if I need to. So impulse equals change of momentum. Impulse equals change of momentum. And momentum is this product m times v. E equal to mv. Okay. So the interesting example with the impulse, with the very basic one, we did a collision of a ball against the wall at a certain angle. I'll do the collision without the angle. So the example for the impulse here that we want to know is if a ball is coming in like this, mv, and it collides with the wall, okay, and it bounces off, and now it's going in that direction, also with the speed mv. And it collided with the wall for a very short time, delta t. Okay, that's right, delta t for the collision. So yeah, then what do we have here? We have F delta t. Okay, so I'll just put a line under here. We have F delta t is equal to the change, so it's the final, all right, P final minus P initial, or F delta t is equal to minus mv minus mv equals minus 2mv. So let's keep going with this example. Now, if I had put a plus x direction to the right, that would have been a good idea, because that's what I was referring to with these minus signs. So now I have, since that's a little bit hidden there, I have F delta t is equal to minus 2 mv. F is equal to minus 2 mv divided by delta t. Okay. Good. The minus sign means the force was to the left. Remember that Newton's third law argument? Who's hitting whom? Well, did the ball hit the wall, or did the wall hit the ball? Okay. Well, the force was to the left, so we could say that was the force that the wall exerted on the ball. To the left, that's why it has that minus sign. And if we had numbers, say 1/10 of a kilogram, 10 meters per second, some short time, then we would actually get the force in newtons, okay? So if you had a problem like this with some numbers, you would solve it this way first, then you would plug the numbers in, it would tell you the force in what? If you use the right units, it would be giving you newtons. So yeah, there's my example. Good. I'm not going to plug in numbers now, but you want to be able to see a problem like this, and when you're given the numbers, you don't panic. You do the problem first, then you plug the numbers in when you're done. Okay. So that's the impulse concept. Very useful and important. We'll leave it at that. Now we have momentum and collisions. This is our next aspect here. And to talk about momentum and collisions, we have to learn about conservation of momentum. If F net comma external, so if the external net force equals 0, then momentum is conserved. I'm talking about a collision between two objects. Net external force is 0, momentum is conserved. You get a whole lot of this at one time. And the law that we're interested in now is the sum of the initial momenta before the collision is equal to the sum of the final momenta after the collision. And 1, 2, 1, and 2. Remember, of course, our convention, the primes are after the collision, the unprimed ones are before or after. And you notice the force drops out of this completely. We don't even know what type of force it was. Went over that a lot with our demos a couple of weeks ago. So yeah, we just have this conservation of linear momentum law. This is conservation of linear momentum. Momentum is conserved. Good. So let's do some examples with the conservation of linear momentum. The one I wanted you to know very well was the collision, the perfectly inelastic collision. Inelastic collision, I'm just going to say inelastic collision. And that's when things collide and stick together. So what we want to be able to do with the inelastic collision is both one and two-dimensional cases. And I can start with the two-dimensional case. I have from this law here, M1 V1 plus M2 V2. If they collide and stick together, they have a common final velocity. So that's how we write this equation out. And remember, this vector equation simply gives us a triangle. So for our collisions at an intersection, for example, I had M1 V1, I had M2 V2. Things collide here. They go off in that direction. This is M1 V, this is M1 plus M2 V prime. And in fact, I don't have to put arrows on the letters here because it's a vector diagram. Okay. Or as a triangle, it's this, M1 V1 plus M2 V2. And you can analyze this triangle. So there, that's the one important thing we really want to know and be able to do. If you're trying, you can just figure this out as triangle. And we did a couple of these. Football player won the car collision. Now, in one dimension, we have the same thing, and we often do it in class. We did it with one particle at rest and the other one moving. One dimension. However, I'm just going to write it out the way we have it without the vectors on it. Or a second example, the one we did the most with, M1 V1 equals the sum of the masses V prime. This second one is when the target is at rest and you've got the incoming particle colliding with the target that's at rest, and that's why V2 is initially 0, and then we get this equation here. So there's an example. Remember, you're not memorizing these, you're just recognizing them and how to use them. The very important thing is energy was not conserved in these collisions. Energy is not conserved. Not conserved. We talked about heat being generated when you with friction or when you pound on a nail or what have you. So the thermal physics chapter is going to start discussing these things. At the time here, we just know that the energy is lost, in quotes. Okay, so energy is not conserved. You want to be able to calculate kinetic energy prime minus kinetic energy initial. Okay. Final minus initial kinetic energy, and 1/2 M1 plus M2 V prime squared minus 1/2 M1 V1 squared, right? That's basically the difference there. And of course you have to use this equation to deal with it. Okay, but I just put the definitions up here, difference in those two kinetic energies. Now, the application of this that's so important is the ballistic pendulum. So let's remind ourselves about the ballistic pendulum. And there are a couple different versions of the ballistic pendulum, so I want to go over these. The first one, I never got to demonstrate it to you guys. That ping pong ball can that I had mentioned. Yeah, if I were to bring that and film it, we really wouldn't see anything. Be that as it may. Okay, ballistic pendulum was to measure the speed of a bullet. So you've got MV here for the bullet. It collides with a big block of wood, capital M, that can then be made to, or it's suspended so that it swings up. So it collides here, and then the whole thing swings up, say to here. And what was so important on the ballistic pendulum is you had energy, no, first you had momentum conservation, but not energy conservation. Then after this block got moving, it just swings up to its old, to its height h, using the basic energy conservation problem. So you want to know this ballistic pendulum. So the momentum we had, mv equals sum of these two masses v prime, and afterwards, after the collision, we had the energy where the block plus the bullet kinetic energy is turned into potential energy. Okay, the way we used to do it. Okay, so that's one example of the ballistic pendulum. Another example, I think I did this as a quiz. Did I do this as a quiz in my lab? Anyway, I've done this as a lab quiz before. So suppose we roll a car off a ramp, car number 1, and it collides with car number 2 at rest. And then they stick together and roll up the hill and finally come to a stop. Given this initial height h, what's this height h prime going to be? Well, you can see this is actually the same thing as a ballistic pendulum problem, except you're going to get your speed from the original height here, but right before it collides on the level, it's got, M1 and V1. They stick together, they have this V prime, they go up here in that V prime, then you would literally just be using this second equation here, okay? Except with M1 and M2, so lower enough case. So that's the second example of ballistic pendulum. You want to be able to do either one. I could give one of these to one class and one of these to the other, that type of thing. So definitely have to know these both. Ballistic pendulum problems. There's a third version of this that's really interesting, and it was in the book. And that is, I don't know if I assigned it, but if you fire a bullet at some object and it goes through, it keeps moving. That's not impossible, right? So let's analyze that. This is a problem in the book. I think you'd even find it. I may have assigned it. So you've got, say I got a ball here hanging from, I'm just going to use capital and lowercase m again. You fire a bullet through here, okay, you've got MV, this thing's hanging here at rest, but the bullet goes through. Say it comes out with half its original speed. So this is initially, finally, on this side, you've got m times v over 2. So there's no external force here. The gravity's not playing a role. This thing just firing along horizontally for this duration at least. So the analysis of this one is really interesting. You've got the momentum, and you could say before the collision I have mv. After the collision, I have the bullet mv over 2, but the ball must have also gotten a kick. Even though the bullet went through, the ball got a kick, so there's capital M, and I'll call that, I'll say that one has a v prime. So there's your momentum conservation equation. Now you could forget about the bullet, it's gone, do its thing, but you could figure out what v prime is based on this here. Okay, this equation tells you what v prime is, so all right, v prime equals question mark. Okay, and then you could ask, okay, how high will this thing swing? Well, that's kind of trivial again. Given the v prime, so h prime is equal to v prime squared over 2g. I'm just writing this down because we've done it so often. Of course, if you need to use conservation of energy, write the whole thing down, figure that out. So h for the ball. Yeah, and if it gave it enough momentum, the thing might swing around, do a loop-the-loop. So there's a nice application as well. So that's the linear momentum. Let's see, I think we can declare that that's what I want you to know for chapter 6. So we're on to chapter 7. Let's see how much time we expect here. Whoa, apparently we're in 47 minutes. Yeah, I don't want to make these too long. So here's what we'll do. We will say that we've finished the review of chapter 6. I call this a thorough chapter 6 review as far as our exam goes. And next time we'll do chapters 7, 8, and 9. And I'll get right to it and make sure that we have everything that we need. In the meantime, you've got this to practice, all of these. Practice them and know them. You can also read ahead, of course, because there won't be any surprises. My chapter 7 review is going to be things we've done before. You can read ahead, practice that. Same for chapter 8 and 9. In fact, I'll narrow things down, right? There's still a lot of material in those chapters. Okay, good. So see you guys next time. And as always, take good notes.